At the end of the previous video, we looked at two examples where we determined all of the local extrema of two particular functions. And we saw that we were able to do this algebraically by looking at the form of the particular functions and being able to determine that the critical points gave either a local min, a local max, or a saddle point by using definitions of those things. In general, that's almost impossible to do. And so our goal is to find some systematic way to check if a critical point gives a local min, a local max, or a saddle point. And that's what we're going to do here to start this video. And so to do this, we do need to make a definition of an expression. So we're going to assume, for the purposes of this definition, that the second order partial derivatives of my function f of xy that we're studying are continuous. All right, this is typically true. There are functions where this is not true, but almost always this is not something we need to worry about. So in this setting, we're going to define the discriminant or sometimes in other contexts referred to as the Hessian, although I won't use that word again. So the discriminant of f of xy is the expression, just going to write capital D. It's going to be the determinant of the matrix where we have all of our partial derivatives as our entries. So our derivatives where we differentiate x first are along the top row, differentiating y first along the second row. And so we can compute this pretty quickly. This is going to be fxx multiplied by fyy minus fxy f of yx. Right? Now, we can even make this a little bit nicer by remembering that under the assumption that second order partial derivatives are continuous, we have Clarice Theorem, which tells us that the second order partial derivatives are equal. And so this would just be fxx fyy minus f of f sub xy squared. Right? So this is Clarice Theorem saying the second order partial derivatives are equal. Right? And so given a function of two variables, this quantity fxx fyy minus fxy squared is called the discriminant of that function. And it turns out that this expression is one of the key factors in whether a function has a local min or a local max at a critical point. Right? So we need something like the first or second derivative test for extrema for single variable functions to help us classify our critical points. And so luckily we do have such a thing, and we call it the second derivative test. All right, so what we need to do for this test, we do need to assume that the second order partials are continuous. And we need to assume that the first derivatives are both equal to 0 at our point AB. So fxab is equal to 0, and that is equal to f of yab. Right? So this is very much like the second derivative test in single variable calculus. This is only going to apply to critical points where the first derivatives are both 0. If we have a critical point where one of the derivatives is undefined, we're going to have to do something else to determine if it's a local min or a max. But that's not going to be a case that appears too often. So under these two assumptions, that the second order partials are continuous and that the first order partials are both 0 at our particular critical point, we have four possible outcomes. So first, if the second order derivative f(x(x) is positive, and our discriminant d, which we just defined, is positive at the point AB. So this means if we plug AB into both the second derivative f(x(x) and the discriminant, we get both positive values. Well, then f is going to have a local min at the point AB. Right, so this is how we're going to check if something is a local minimum. We're going to check if the second derivative f(x(x) and the discriminant are both positive. Right. On the other hand, if f(x(x) is negative and the discriminant is positive at our point, then f has a local max at the point AB. The third possibility, if d is negative, if the discriminant d is negative at AB, then f is going to have a saddle point at AB, right? And there's only one other case to consider. If you look through these three, you notice that case 1 and 2 take care of what happens when the discriminant is a positive number. Right? If the discriminant is positive, either that first derivative has to be 0 or positive or negative. If d is less than 0, then, if d is less than 0, then we have the saddle point. The only other possibility is what happens if d is equal to 0. And the answer is that the test is inconclusive. Right? And so again, we'd have to do something else. This is very similar to the second derivative test for Extrema. For single variable functions, it obviously has the little bit added in with the discriminant. That's because we have multiple variables now. But it is very similar. The discriminant is what determines whether we have a local extreme value or a saddle point. As you can see, the discriminant being negative says saddle point. If the discriminant is positive, then we have either a local min or a max. And in this case, if we know we have a local extreme value, the derivative f(x(x) determines if we have a local min or a local max. So let's look at a couple examples. So first example, let's find all the local extrema of the function f of xy equals 6y squared minus 2y cubed plus 3x squared minus 6xy. Right, so the first thing we should do is just to point out that this function is a polynomial in two variables, x and y. And so because of that, I know the second partial orders, or second partial derivatives, are going to be continuous. Right? So we can definitely apply the second derivative test that we just saw. So I don't often write this down even explicitly. A lot of times we are going to be dealing with continuous functions, but it is worth just double checking to make sure that before we go down this road to try to use the second derivative test, that it does actually apply. And so we want to find all of our local extrema. So the next step is to find our critical points. So we find our partial derivative. So f sub x is going to be 6x minus 6y. F sub y is going to be 12y minus 6y squared minus 6x. right? And so both of these are polynomials, so they're both going to exist everywhere. There's no points where they don't exist, so the only critical points will come from when these are equal to 0. So we'll set both equal to 0. Now the first equation, if I solve this one, 6x minus 6y equals 0, we're going to get 6x equals 6y, and therefore x has to equal y. So unlike the previous examples we saw in the other video where we ended up with just an x equals a number here, the first partial being equal to 0 only tells us that x and y have to be equal, but that actually gives us infinitely many possibilities for critical points. Of course, we also need the second of our first derivatives, f sub y, to be equal to 0. So we also have to account for that. But notice that in order to solve this second equation, 12y minus 6y squared minus 6x equals 0, we have to find some relation between x and y, and that's exactly what we just did. We just showed that x and y are exactly equal. So this second equation, this 6x here, is the same thing as 6y. And so what we really have, when we rearrange this, and I'm going to move everything to the other side to make the y squared term positive, this is the equation 6y squared minus 6y equals 0. Right, and we can solve this pretty easily. We can divide both sides by 6 to get y squared minus y equals 0, and we can factor out the y. And so we have to get one of these two factors equal to 0. And so we have two options. We have y equals 0, and we have y equal 1. All right, those are our two values of y that could possibly be critical points. But remember that we also know that x has to equal y. And so we end up here with two critical points. We end up with the origin, 0, 0, and we end up with the point 1, 1. Right? And so we know that these are the only possible local extrema, and now we're going to use the second derivative test to determine, to classify each of these as local extrema. All right, so the first thing we want to do is compute the discriminant. And so we look back at our partial derivatives, fx and fy, and so we have to compute all of our second order partials. So fxx is we have to differentiate 6x minus 6y with respect to x, and we just get a constant 6. Fyy, we're going to differentiate 12y minus 6y squared minus 6x with respect to y, and when we do that, we get 12 minus 12y. Oops, sorry. 12 minus 12y. And fxy, we know from Clarice Theorem we can differentiate either derivative with respect to the other variable. So I'm just going to differentiate fx with respect to y, and we get negative 6. Right? You could do that the same way if you did f sub yx. Really doesn't matter which way you go with that one. And so our discriminant is going to be fxx fyy minus fxy squared. So we end up with 6 times 12 minus 12y minus negative 6 squared. And so when we combine all of this, we're going to get negative 72y plus 36. So this will be our discriminant expression, that's at negative 72y plus 36. Right? And so when we go to evaluate our discriminant at our two critical points, we just have to evaluate it at this particular one, or for this particular expression. So the discriminant of 0, 0 is going to be, of course, negative 72 times 0 plus 36, which is 36, which is positive. So at this point, I know that at the origin, we're either going to have a local min or a local max. That part's determined by the discriminant being positive. Whether it's a local min or local max is determined by f sub xx. Right? And so up here, we've already seen that fxx, that partial derivative, is equal to 6. And that's at any point. Notice if this were a formula involving x and y, we would just replace x and y with 0, 0 with our point. But in this case, it's a constant function. And so we know that that is positive. And so when the discriminant is positive and the partial derivative fxx is positive, then what we have is a local min at the point 0, 0. So we have a local minimum at the origin. Right? Our other critical point was 1, 1. So we'll compute the discriminant there. So d1, 1. All right, so that'll be negative 72 times 1 plus 36. That will be negative 36. And negative 36 is a negative number. And when the discriminant is negative, we don't care about the partials at all. That tells us right away that we have a saddle point at the point 1, 1. And so we saw that these are the only two values that we need to consider. These were the only two critical points. And in this example, using the second derivative test, we see that we have a local min at the origin and a saddle point at the point 1, 1, and no local maximum anywhere in sight. Let's look at one more example. This one will be a little bit more complicated. So let's find all the local extrema of the function f of xy given by 6y plus 3xy minus 3x squared y minus 2y squared minus xy squared plus x squared y squared. All right, now once again, I look at that, I see that it's a polynomial, so I'm comfortable with the fact that all of our partials are going to be continuous, and so we can use our second derivative test. So the first step is to compute our partial derivatives. So f sub x, if we just differentiate across, we're going to get 3y minus 6xy minus y squared plus 2xy squared. And for our partial y, f sub y, we're going to have 6 plus 3x minus 3x squared minus 4y minus 2xy plus 2x squared y. Right, so what we need to do is we need to be able to set each of these equal to 0 and factor the left sides of each of these equations. And we can factor each of these left sides by using factoring by grouping. Right? So for f sub x equals 0, we have 3y minus 6xy minus y squared plus 2xy squared equals 0. Right, so the first thing we can do is we notice every term has a factor of y, and so we can factor out a common factor of y. So what's left is 3 minus 6x minus y plus 2xy. Right, and then this 4-term polynomial in parentheses we can factor by grouping. And so we look at our first two terms, 3 minus x squared, and we want to pull out the largest factor from those two terms, which would be 3. And what's left is 1 minus 2x. And then we do the same thing for the third and the fourth term, the last two terms. We want to factor out the largest common factor, which would be negative y. And when we pull out negative y, we get a 1 minus 2x. And now in the brackets, we have two terms. Each of them have a factor of 1 minus 2x. And so we can factor out 1 minus 2x, and our remaining pieces are 3 minus x. Or I'm sorry, 3 minus y. And so we see we have three solutions to f sub x equals 0. We have x equaling 1/2. That comes from 1 minus 2x being equal to 0. We have y equals 0. And we have y equals 3. Right? So we have these three possible values from f sub x. Right? And so at this point, there's a few different ways we can proceed. Remember, the goal is to find all the points where f sub x and f sub y are equal to 0. And these are the three values where f sub x is equal to 0. And so the approach I'm going to take is I'm going to take each of these three values, the one value of x and the two values of y, and I'm going to substitute them into f sub y. And given each of these, we're going to then determine what values would make f sub y equal to 0. Now, in order to make that easier to do, particularly when the x is 1/2, because we're actually going to have to evaluate that expression when x is 1/2, it's really helpful if we go ahead and factor f sub y. And so I'm not going to go through this process. It's very similar to what we just did. But I had on the previous screen, I had what f sub y was equal to, just a polynomial, I believe, of 6 terms. And so go ahead and try it on your own to make sure you remember this grouping technique. But when you do, you should get f sub y equaling 2y minus 3, x minus 2, and x plus 1. Right, so you should get f sub y equals these three. Right, and so again, we want this to equal 0. And so my approach that I'm going to take is I'm going to take each of these three values individually, substitute them into that expression on the left side of f sub y equals 0, and then solve for the remaining variable. So to illustrate what I mean by that, I want to pick one of our values that makes our partial with respect to x equal to 0, which is x equals 1/2, and I'm going to substitute this into the factored form of f sub y equals 0. And when I do that, we get 2y minus 3. The next term is 1/2 minus 2, which is negative 3/2. And the last term is 1/2 plus 1, which is positive 3/2. Right, and we want that to equal 0. And so this equation, these constants can be divided out on both sides. And so really we just have 2y minus 3 equal to 0. And so this gives us y equal to 3/2. And so what we have, I'm just going to make a list down at the bottom of the screen of my critical points. What we've just seen here is that when x is 1/2, we will have a y value of 3/2, and this will make both of our first order partials equal to 0. X being 1/2 will make f sub x equal to 0, and x being 1/2 and y being 3/2 will make f sub y equal to 0. So both partial derivatives will be 0 in this case. But that's the only point with an x being equal to 1/2. Now, our other two possibilities from solving f sub x equals 0 involve y. So, for example, we have y equals 0 as one of our options. So we know f sub x is 0 in that case. So I'm going to substitute y equals 0 into the equation f sub y equals 0. And when I do that, the first term is a negative 3. It's 2 times 0 minus 3. And the other terms, x minus 2 and x minus 1, are unchanged because they are in terms of x. I'm sorry, that should be x plus 1, not x minus 1. All right, so we have this equation here, and the negative 3 doesn't play any role. We can divide out by that constant. And so we see we have two possible values of x here. We can either have 2 or negative 1. Both of those will make f sub y equal to 0. And so we have two critical points here. We have the point 2, 0. That's x being 2 and y being 0. And we also have the point negative 1, 0. All right, so y equals 0 gives us two different critical points. Right? And similarly, y equals 3. When we substitute that into the equation, f sub y equals 0, we get 3 times x minus 2, x plus 1. Only that first term is changed. Only the first factor has changed because it's the only one that involves y. And again, we're going to get the same two values of x. And so this gives us two more critical points. We have 2, 3 and negative 1, 3. And so this list of 5 critical points is our entire list. And we did this by taking f sub x equal to 0, finding the 3 possibilities for that equation to be 0. And x is 1/2, y is 0 or 3. And then we took each of those and substituted it in to f sub y equal to 0 and found when that equation was also equal to 0. We could have certainly approached it the other way. We could have found when f sub y was equal to 0, then substituted each of those possibilities into the equation f sub x equal to 0, and we would have ended up with the same 5 critical points. And so when there are a lot of critical points like this, when there's lots of possibilities for x and y, this is one approach that you can take, is to solve one of the 2 equations that you need, take those values and substitute them into the other, and then solve that second equation, and that should give you all the critical points. So now that we have all of our critical points, we can pretty quickly apply the second derivative test. So we need to find our second order partial derivatives. So looking at our original expression for f sub x, if we differentiate in terms of x again, we're going to end up with negative 6y plus 2y squared. For f sub yy, right, our partial of f with respect to y differentiated with respect to y again, we're going to get negative 4 minus 2x plus 2x squared. Right, we also need to know f sub xy, one of the second order mixed partials. And so if we differentiate f sub x with respect to y, we will get 3 minus 6x minus 2y plus 4xy. Right. So from this, we do know that our discriminant is going to be f sub xx, f sub yy, minus fx sub xy squared. Now, because these are really nasty expressions, I'm not going to try to multiply all of that out and get a single formula. I'm just going to apply it in each particular case to each point. So, for example, one of our critical points was the point 2, 0. And so we're going to compute what happens at the point 2, 0. And so at 2, 0, I know, so f sub xx of 2, 0, if we substitute it into f sub xx, because f xx only involves y, this ends up being 0. And so I don't really care about f sub yy, because whatever that is, we're going to get 0 multiplied by that. And so I also need to know fxy, the mixed partial. And so if I substitute 2, 0 into that, we're going to get 3 minus 6 times 2 is 12. And the other two terms involve 0, the y, and so it's just 3 minus 12, which is negative 9. And so our discriminant value of 2, 0 is going to be 0 times whatever the heck fyy of 2, 0 is. Like I said, I don't care because it's being multiplied by 0, subtracted by, or subtracting from that, negative 9 squared. And so when we do this, we get negative 81, and that is a negative number. And so the discriminant at 2, 0 is a negative number, and so that tells us that we have a saddle point at the point 2, 0. Now, I'm going to let you try the rest of these on your own. I'll tell you what the answers are, but just the actual evaluation part, it's just very tedious. None of this is difficult. It's substituting particular x and y values into the 3 second order partials at the top and subtracting and determining if that number is positive or negative. But it turns out that you will also get saddle points at negative 1, 0, negative 2, 3, and negative 1, 3. Right? So you will have saddle points at all 4 of those values. In fact, I believe the discriminant in each case is actually equal to negative 81. So I believe you, which is not necessarily always, is mostly a coincidence than something that will always happen. You could certainly get other negative values of the discriminant there, but I believe in this case all 4 of these have the same discriminant value. However, when you compute the discriminant of the point 1/2, 3/2, you will get 81/4, which is a positive number. So then we have to go back to f sub xx. All right, so let me actually write this down. So d of 1/2, 3/2 will be 81/4, which is positive. So then we have to go back to f sub xx and determine if this is positive. So we know we do have a local extreme value here. And when you plug these into f sub xx, you will end up with the number negative 9/2. And that is a negative number. And so what that tells us is that we have a local max value at the point 1/2, 3/2. Right? And so this classifies all 5 of our critical points that we found. 4 of them are saddle points, and 1 of them is a local max. And it's really not, other than the arithmetic is just a little bit, disgusting, particularly with the fractions, just kind of tedious to do, but it is not very difficult to do. All right, so even with a more complicated function like this, it's really just algebra and arithmetic and a little bit of tedious work.